Thank you, Siva and Anita, for this invitation. It's really a pleasure to talk around such an enthusiastic audience. So this is the second year, and I hope this year's audience is even more enthusiastic and interesting than the last year's. So now, as a talk, so we'll start with the talk. So this talk will, as the title suggests, we will be looking at the number e. So you all would have been familiar with the number e? Yes? And in fact, there are a few mathematical constants that you have been, that are interesting and you would have been introduced to. So can you name me the other constant? Pi. Everybody knows pi, and pi, in fact, you would have been introduced before you were introduced to E. So today, and we know at least what is pi. Pi is has attracted fairly big attention. There's a Pi Day, but unfortunately, our small e, that has not basically attracted that much of attention. So there's no E Day or nothing like that, and it pops up everywhere. But we really, so maybe we don't have an idea. Maybe we have an idea. What is that number? So now, what is your idea of E? What is E? So, yes, so I can hear some voices. It's an irrational number. So, yes, that is a very big point. But is this just a number? And if it is just a number, why does it pop up everywhere? If you'll see in statistics, if you'll see in probability, in mathematics, in physics, you'll see everywhere. So you would have seen in physics radioactive decay, you would have seen exponential function in mathematics, the normal distribution in probability. So it pops up everywhere. So is it just a number? So it's just a number, 2.7 something, 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 something. Or it has some meaning to it. And where did it come from? So today, basically, we will be looking at these questions, that where this E has come from. And so what will we do? We'll look at a brief we'll go into, peep into history of E, briefly, till we find it easy and simple and beautiful for us. So basically what will we do? You had 3 problem sessions on calculus. So this is again something on calculus. But now today, in this hour, what will we do? We'll just focus on beauty of mathematics, the ideas that how they developed, rather than the rigor. So here, what I will presenting would be not as rigorous, but we'll see how our great ancestors had beautiful ideas, and that led to such a well-developed theory at present that we are using. So now we start with so now one thing that we have is that E is the base of natural logarithm. So if we are talking of E, we will talk of log also. Yes? And now this thing, we see that it's not a new thing, the concept of log. It was way back 2000 years ago. So the problem, in fact, that hint, without the people being aware at that time what they are up to, that popped up in Mesopotamia. So in Mesopotamian tablets, we could see that the problems that they were considering, so this investment problems, were basically looking at, so a typical problem that we picked up from Mesopotamian tablet, that there is a sum of money, so invested at an interest rate of 20%, compounded annually. So how much time it will take to double that money? So you all would have done compound interest, yes, in school. So you remember the formula? Or you can, So basically, just think of that you remember or not, but now if you don't, try to recall it, but let us, so basically what will you want? You will like to look at the the thing that you would like to look at would be that you have principal, some invested is P, and you will look at that 1 plus, so 20 is percent, so 20 by 100 to the power T should be 2P. So basically what you would like to have to solve a problem of the kind 1.2 power T is equal to 2. Yes? How will you solve this? How will you solve this problem? You will take, so now here the log tables come into picture when we are solving it. Yes? So you would have been aware of log tables also. You would have used in your schools again. So now, but Babylonians did not know log tables. So see how smart they were. They did not know log tables. So when we compute this, this comes out to be 3.80 something something, just by using log tables. And Babylonians, though they did not know logarithms, but and they did not know there's one thing that will be introduced to interpolation. They did not know that also, but they actually applied interpolation in a way to get the value 3.7 something, 3.78, and that's remarkably well. Without knowing the knowledge of logs, it was so. Now, so there's almost the first appearance of the relevance of log came into picture, but that time it was not felt. Now we will again pursue the problem of compound interest, and now we will look at the typical problem, the very first basic thing of compound interest. So we have a principal amount P invested at a rate of R% compounded annually for T years. So now exactly I am just asking you the formula for compound interest that I've used also here, in fact. So that's almost written here, isn't it? So it is, so what is the formula for compound interest now? P times 1 plus R by 100 to the power T. Yes? Now I do an easy work. I don't want to go into, so I take P is equal to 1. You can take it as 1 lakh rupees, 1 rupee, 1 cent, whatever you want. So P to be 1, R to be 100, that is the best I can think of. That okay, my money gets doubled after 1 year. And T to be 1. So that means then, therefore, what I'm getting the amount of 2 back after 1 year. Now, some bank wants to attract me and tells me that, okay, instead of compounding it once in 1 year, what we'll do is we'll compound it 2. So now basically,
you're one slide ahead.
I'm having one slide ahead. Yeah. So basically now instead of the compounding it once, we compound it twice for you. But what will we do? We won't put the 100% interest at the end of 6 months because we are compounding it twice at the end of 6 months, half of the period. So we'll basically have the interest rate as also 100 by 2. So 50% interest rate at the end of 6 months, and we compound it twice. So after 1 year, what will be the amount? So now that will be again, so here it would be 1 plus 1 by 2 whole square because it's compounded twice. So twice it will happen. So, and that comes out to be 2.25. and I see that, okay, there is some benefit in compounding it twice. And I become more adventurous and say, oh, I wanted compounded to be thrice in 1 year. And then what I get, that I have the amount back would be 1 plus 1 by 3 whole cube, and that is 2.37. And now my greed increases. So now I'm greedy. I say that, okay, why 3? Why not go to 4? Or why not go to 12? Compound it every month. Or why not go to every week? Compound it every week. So n equal to 52. Or why not compound it every day? So now, in general, now I calculate, I see that what will be the benefit that I'll get. So if I ask the bank to compound it n times, obviously the condition being that the interest rate is 100 by n in that period. So then I will have the amount that I'll get back is 1 plus 1 by n to the power n. Yes? All agreed? So now I see that, okay, let me see what will be the n that I should stop at. So I just do random calculations with my calculator, and I try out n equal to 10, 100, 1000, 10,000, 1 lakh, and I see, oh, as I go on increasing n, my amount that I'm getting back, Sn, is increasing. But at the same time, I also see one more thing here. So what is the thing that so it's increasing, all right? But the difference between Sns is growing smaller and smaller. Now I am at least I know decent mathematics. I see that as n goes larger and larger, the difference is not very high. Yes? So maybe it converges, that gives me a tinkling that maybe it converges to some point, some number. So what basically, so now I say, okay, I just observe the first thing, that as n increases, my Sn increases. So I say that, okay, I want the interest to be compounded every instant. So every instant my money is being compounded. So what will be that thing? How will I calculate that the money that I'll get back if it is compounded every instant? If it is continuously compounded. Just any guesses? So what I'm doing, what is happening to n? N is increasing and n is going to then infinity. So what basically should be the amount that should be limit n goes to infinity of Sn, that is 1 plus 1 by n power n. And this limit, in fact, is the number e. So what is e basically is the amount that I'm getting back if let us say that's 1 rupee, let us just play a little small. So if my 1 rupee is compounded continuously for 1 year, then I'm getting e rupees back. So that is my e. So that was okay, so as to say, but as a mathematician, what will be the question that you will have? Does this limit really exist? You're talking of that, okay, this limit is e and all those fancy things. You're defining also e as limit 1 plus 1 by n power n now. But does this limit really exist? So in fact, we can prove easily that this limit exists. But again, as I had promised, I won't be going to the very rigorous notion of this limit being existing on so. So what will basically show is that Sn as this 1 plus 1 by n power n is monotonically increasing and bounded, and therefore it should be convergent. But what I'll do instead, I'll connect it with another limit. So what I'll do is, I'll show that this limit exists through an indirect way, and that's also not very rigorous. We just have ideas. Okay. So you all know binomial theorem, 1 plus x whole power n. Yes. And now if I take x to be 1 by n, I'm getting 1 plus 1 by n power n. And that will basically turn out to be, because my first two terms are 1, so 2 plus some 1 by k factorial. So now what do you have? N choose k, 1 by n power k. So what I do is, I write n choose k, what I can write n choose k as n minus 1. So I can write my n choose k as n minus 1 till n minus k minus 1 by n power k, and 1 by k factorial here. And just divide, plug in this n with every term. So you'll get, what is this? Some 2 plus some 1 by k factorial, 1 minus 1 by n, 1 minus 2 by n, 1 minus k minus 1 by n. And now, because my focus is just the limiting value as n goes to infinity. So for fixed k, this product, because for a fixed k, k by n goes to 0. That's simple, that you all would be knowing. So my product 1 minus 1 by n, 1 minus 2 by n, 1 minus k by n, that goes to 1. Yes? So I have that. This basically, now what is happening? Now see, what I am taking is 1 plus 1 by n is 2 plus some k from 2 to n. So n is going to infinity. So that becomes k from 2 to infinity. And I have the product terms are 1. So this basically turns out to be that in the limiting case, my limit as n goes to infinity, 1 plus 1 by n power n is nothing but the sum of this series 1 by k factorial. So you're all, have you seen this series? Yes? You're all familiar with this series? You know why so I've written a little hint also. So almost the easiest one, that why we can how we can see that this series converges. But have you done that this series is convergent? So basically, see now, you're aware of geometric series? Yes? And you know that a geometric series summation r power k will converge if and only if mod r is less than 1. Yes? So, and also, now what I have, if I have a series summation xn, let us say, and I have 0 is less than xn is less than some r power n, less than equal to some r power n for all n, then at least intuitively, if you do not, you can see that sum over xn's if I take will be less than equal to sum over r power n. And if mod r is less than 1, we know that my summation xn will also converge. So again, I'm not going into the the details of it, but this is the idea actually. So just a little, very few technical details, just the terminology that when we do infinite series, that comes into picture, but this is the idea. Yes? So we are convinced that summation 1 by k factorial, this is some number, this infinite sum is a real number, and that real number also we call as E. So now it's not just a number, an irrational number, but it is limit of a sequence 1 plus 1 by n power n, and sum of the series 1 by k factorial. Yes? So this is almost the definition of E, that the way we define our E. Okay, so now we started from that when I'm talking of E, I cannot ignore log. So, and I said that, oh, Babylonians did not know log. But, whoa, so who propounded log? So if in 1617, almost, so 1,000 years back after Babylonians, in fact, now John Napier propounded publicly the notion of log. And why did he do that? So now see, we have calculators, computers at our command, and we can really do calculations in seconds, in fraction of seconds, big complicated calculations also. But way back in hundreds of years ago, there were no calculators or nothing. And people used to do big calculations by hand. So to ease out the trigonometric calculations, John Napier came up with the idea of log. So in fact, he made his first log tables in 20 years by calculating everything by hand. So, but what was the key observation that led him to develop this notion? So he saw that if I'm multiplying two numbers, a power n, a power m, then this is just a power n plus m. So basically what is happening is, the problem of product, taking the product, is reduced to the problem of taking the sum of the exponents, if we know the exponents. Similarly, the problem of division will reduce to the problem of subtraction. So now if you know the exponent, that will help. So that was his key observation that led to the whole theory. But now, so see, when we have a concept, it takes time, and it's not just, often it's not just a result of one person's labor, but many people are involved. So it's a slow, gradual process for every beautiful theory to develop. So here, what was his log? So we are calling it Nap log. So Napier log, that was, so if y is equal to Nap log x, so that's something different from what we do. So 10 power 7, 1 minus 10 power minus 7 to the power y is equal to x. So that was his Nap log. But just 3 years afterwards, Henry Briggs came up with the base 10 logarithm that we use in computations, in fact. So that was a theory of log. So now you remember, so in 1617, the notion of log was there, and they were not, that was very clear that the base is something that can be changed. So that was very well understood, that it's not that 10 is something that's very special. I can consider now log to any base I want. That is simpler for me. Okay, so that was being understood. So now remember, they had the notion of log in 1617 at least. So now we come to another kind of problem where this beautiful E will come up. So there is a problem of squaring planar shapes. That means finding the area of planar shapes. And see, that was basically the, finding the area of different shapes, different regions. That was the Greek mathematicians basically studied these kind of problems extensively. So, and Archimedes, in fact, in 200 BC, calculated the areas of circle, parabolas, but hyperbola was one of the, conic sections. So conic sections has circle, ellipse, and hyperbola, parabola. So conic sections were they were able to handle conic sections way back in 200 BC, except hyperbola. So hyperbola, the area, so what do we mean by the area of hyperbola? The area under the curve of hyperbola. So that was not basically, could not be computed. So that was and that remained uncomputed for a long time. So now okay, so when now if I ask you to find area under some curve, what do you do really? Integrate it, exactly. Now remember one thing more. That time integral calculus was not introduced. Newton introduced it in later half of 17th century. So this is, we are in the first half of 17th century. And in fact, these are the notions, these are the gradual developments, as we say, that led to the development of integral calculus. So now Fermat, basically, so remember Archimedes had calculated the area of a parabola, y is equal to x square. So Fermat, what did he do? He calculated the areas under the curve for y is equal to x power n. And we'll see how he calculated. So now you have a well-developed notion of integral. You know how this the integral of a function is defined. It signifies the area under the curve of that under the curve of that function. That's all right. We all know. But again, Fermat did not know those things. And those people, those basically focused on the ideas and the beauty of mathematics rather than rigor. So rigor came gradually with their ideas. Okay, so here we'll see how Fermat basically computed the area under the curve y is equal to x power n. So what did he do? So now we'll look at, so we are having, so here you can see a figure for y is equal to x cube. What did he do? Here he wants to, so now we want to calculate the area under the curve y is equal to x power n or x cube from bounded by x is equal to 0 and x is equal to a. Now for you this is a simple task. You will just, what will do? You will integrate x power n from 0 to a, and that will be a power n plus 1 by n plus 1. But how did Fermat do? Let's see what basically was going in his mind. So what did he do is, he considered, so now you will see, I've marked some points A, B, C, D, E. So A, he started with this A0, the point, and then he took R less than 1. Okay, so R something positive number which is less than 1, and he considered the points AR0, AR square 0. So now my B is AR comma 0 on the X, C is AR square 0, D is AR cube 0, and because R is less than 1, I am moving towards the left. Yes? So my B is towards the left of A, C is towards the left of B, and so on. And now, say, how do you integrate? What was also the first principle of integration? You divide the interval into, partition the interval into finitely many subintervals. And then, so for example, 0, 1, if you're having the interval, you'll just take 1 by n and then consider n going to infinity. Yes? But what did he do? Now see, will this interval be, so if I'll just keep on taking AR power k plus 1 and so on, this will all be greater than 0. Yes? So basically what he's doing, he is dividing the interval into infinitely many subintervals. Now he didn't think of rigor, he didn't think of that whether it is allowed or not. He just did that. And he knew how to calculate the sum of a geometric series. Okay, so now what he basically found, so now see, we are having rectangles. The rectangles, what I am having, I'm taking, so the rectangles are bigger than the hyperbola. The sum of the areas of the rectangles will be greater than the sum that I require, that is the colored portion. Yes? But if I take R near enough to 1, If I keep on increasing my r and make it closer and closer to 1, what will happen? Just visualize. What will happen? If I'm taking r closer and closer to 1, the width of the rectangle keeps on decreasing. Yes. And the height? Height also will. So now what will happen? So let's see. So I have this function, and I'm just having a crude thing. So, that's here. Okay. Okay. So what we do is, let us take. We take this function, this thing, and now we have, when I have r to be, so what, now I take on smaller and smaller r, oh sorry, bigger and bigger r, so what will happen? This, my r is now this, and then it is this. So the extra area that I was computing in the rectangles is decreasing. That's the notion that you do in your actual integration also. What is the first principle? What do you do when you're taking the intervals and subdividing the intervals into n parts and then taking n to infinity? Basically, you're having the sum of the areas of those rectangles, and as n goes to infinity, as the width decreases, that the extra portion or the less portion, that basically vanishes. So the area is nearly equal to the required area. Yes, and that happens here as well. Okay, so as r will go to 1, the difference between basically the extra portions will become smaller and smaller and smaller, and finally, as in the limiting case, it will be same as the area that I require. So now let us first calculate the area of the rectangles. So what is the width of the rectangle? So let us just take AB, with the rectangle with the base AB. The width is A minus AR. Yes? Width, what is B? B is AR, A is A. So the width of AB is A minus AR. Where is the duster? So this is A minus AR. So this is A, 1 minus R. And what is the height? Height is the functional value at B. That is, sorry. It's a functional value at A. So this is A power n. So what will be the area of the rectangle with base AB? That will be A, 1 minus R, A power n. Again, now for BC, what will you do? This will be the width will be AR, 1 minus R, AR power n. Yes? So basically, you are doing, keep on doing that. You will see in the slide. So it will become AR power K, 1 minus R, AR power K power n plus whole power n. And therefore, now it becomes a geometric series with common ratio. What will be the common ratio here? A is, anyways, A power n plus 1 is always there, isn't it? So this, if you'll write, it will be A n power n plus 1. So for AB, what will be this? A n power n plus 1, 1 minus R. For BC, it would be, the area would be A power n plus 1, 1 minus R, R power n plus 1. For CD, it would be A power n plus 1, 1 minus R, I'm just calculating, R power n plus 1 square. R power 2 whole power n plus 1 or R power n plus 1 whole power 2. Both are the same things. So what I have, the common ratio is r power n plus 1. And then therefore this infinite series will have the sum as 1 minus, so the common portions is, the common thing, a power n plus 1, 1 minus r was common in all the things. And the sum will be 1 minus r power, yes? Got the hold of it? So, now what is 1 minus r by 1 minus r power n plus 1? So, that is, so you have 1 by, so you're having 1 by 1 plus r plus so on, r power n. And r, as r goes to 1, this is a power n plus 1 by n plus 1. And that is basically Fermat's thing. So we have now better way out to calculate these areas. But now see that again, remember that those were the days he didn't know integral calculus, he didn't know that there was no well-developed notion. He also saw, so no, he observed that this also works for the curves x power minus n, where n is a natural number. Now, obviously, we will take the integral for x greater than some a, positive a. So that he noticed, and calculated and wrote that the area would be a power minus n plus 1 by minus n plus 1. Now, what happens when n is equal to 1? This formula obviously doesn't work, isn't it? So minus n plus 1 will be, so what is the problem? So what now goes wrong with a hyperbola? Let us see. So when n equal to 1, this becomes y is equal to 1 by x. That is a rectangular hyperbola. And let us see what was the problem. So now see. So here how this, so now you know what will the area when I have a hyperbola, says what will be the area under the curve hyperbola that so what the slides requires, this area under the hyperbola y is equal to 1 by x, from x is equal to 1 to x is equal to a. What will be that? What is the area? In your present knowledge, this is integral 1 by x dx from 1 to a, and what is that? So that is the natural log of a. That's it. Now, but yes, that we know, but they didn't know. So what? So let us see, let us try to be with them and see what was the problem with Fermat's thing. So what did he do? Now see, because my x power n's are in the different, the curve is basically when I'm going from 0 to infinity, now this is going to 0, asymptotic to 0. So here I will be starting with my a, let us take a as 1, 1, 0, the point. And now I'll go to the right of my a. So obviously I'll have to take r greater than 1 to go to the right. Then only I'll be able to go to the right. So b will be ar0, c will be ar square 0, and so on. Now see what happens if we exactly apply Fermat's thing. So here, now what will be the width? Again the width will be the same. It will be just a r minus 1 for AB. And what will be the height? The functional value at A, that is just 1. So A is 1, A is also 1. So it will just R minus 1. For BC, what is happening? This is R minus 1 is the width. And what is the height? 1 by R. So what will be the area? Again R minus 1 of the rectangle. Now if I go on, so if I want to apply Fermat's thing, what will happen? This is all constant. You end up taking infinite sum of a constant. And that we know that it's infinity. So there's some flow, isn't it? You can see the area is finite. You can have a square and say that it is less than this area of this square. So now that doesn't follow with the intuition. So there's something wrong. That's not the way to calculate. But now see, so Fermat was very disappointed. He could not calculate the long-standing problem of squaring a hyperbola. But now based on this observation, so basically what is happening? If I'm going from 1 to, so if I'm going to from B to C, so R to R square, my area of the rectangle is increasing. It is becoming from R minus 1 to 2 times R minus 1. Then I have to go from 2C, R cube, then it is getting 3 times R minus 1. So what is happening? If I am increasing my T, so a T, I have this area of a, so if I am increasing my T geometrically, then my area is increasing arithmetically. Yes? And in other words, we can say, write this observation as A of ST is AS plus AT. And this, remember, is the property of the exponents, or so as to call logs. That was the key observation of Napier also. So this was observed by St. Vincent and his co-authors and pupil. Basically, notice that this is the characteristic property of logs. Now log came into picture. Now one thing also, my area AT, if I am calling, that is independent of log. My log, so now there we realize that log has a base. So he is saying that, okay, AT is log of, with the base B of T. But when B will change, the right hand side will change. But AT cannot change. It is not something that is dependent on the value of log. It's just area of some region. So B has to be a fixed unique number. Yes? And this B basically turns out to be E. So this we'll see that beautifully again my E comes up. And this B is nothing but, so B is the unique number such that integral 1 to T 1 by x dx is just log B, 1. So now this B is nothing but E. And that we'll see again, we won't see rigorously. We'll just see, now we'll come to Newton and follow his line of ideas. So you'll see how beautiful, how they just, so mathematics is really beautiful. And actually, they're just dependent on the beauty of it. And the intuition and the beautiful ideas. So let us now follow Newton, Mercator, and so now we are coming to the second half of 17th century. So what we have, so we know this geometric series. See, geometric series was again something known to those people. So we'll see that many of the things is just done by the knowledge of geometric series. So 1 by 1 plus x, we know the series is 1 minus x plus x square minus x cube and so on. Now, what did Newton do? He just integrated on both sides. And he said that, oh, this if I just integrate both sides, I can integrate the series term by term, and that will be just the integral of the sum. The sum of the integrals is integral of the sum of the series. That is actually true, but Newton just applied it without basically worrying about the rigor. But that, remember, that is exactly true. You'll be doing in mathematics. If not, you have not done, then you'll be doing later on. So basically, Now, so the problem is, what is the integral of 1 by 1 plus t? Now, Newton was the father of calculus. He propounded this integral calculus, introduced integral calculus to world. So, but what will be the integral of 1 by 1 plus x or 1 by 1 plus t? So, now one knows that integral is, okay, integral is the area under the curve. So, and we know that the integral area under the curve of 1 by t from 1 to x is log bx. So, this it's a translation. So, that will be the integral, that will be log 1 plus x to the base b. So, b, remember, that came up with the area of the hyperbola. That is the b that I'm using here. So, now one has that log 1 plus x to base b is this series. So, he had the series expansion for this log function. Now, in fact, this was given by Mercator, in fact. So now see, what did Newton do? Newton had a very he had a very standard thing that he used to. He got many series by this method. We are just concerned focus. We are just bothered about the our exponential or E series. So, but that is a standard way that Newton found series expansion for many functions. So, what did he do? He called this as a method of inversion. So, he took the y to be the inverse function of this log 1 plus x, and then that will mean that b power y minus 1 is x. And we know that y is, we know the series expansion for y, x minus x square by 2 plus so on. And now what he did was, he wanted to solve for x in terms of y. So basically what did he do? He wrote x as a0 plus a1y plus a2y square and so on. And now he plugged that value of x in the series for y. So you have on the left hand side y, you have on the right hand side in a way series for in y itself. And then he equated the coefficients of y. So he equated the constant term that gave him that my 0 is a0 minus a0 square by 2 plus so on. And this series is nothing but, we know that this series is log of 1 plus a0 to the base b. And therefore a0 should be 0. Yes? My log of 1 plus x is 0 if only if x is 0. So, and by equating now the different coefficients, he got the values of a1, a2 and so on. And again, see, so he didn't bother about calculating, obviously it's not possible to calculate all the coefficients. He just calculated some initial coefficients and inferred by seeing the pattern that all coefficients be like that. Now he didn't bother about how to prove it, what to do. He just wrote that, okay, now the series would be b power y. So b power y is 1 plus y square by 2 factorial and so on. Now if you see y, take y is equal to 1. What do you get? You get the series 1 plus 1 by 2, 1 plus 1 by 2, 1 by 1 factorial plus 1 by 2 factorial plus so on. And that is exactly E. So my B comes out to be nothing but E. So here my E comes into picture. So now we know that base, that the integral 1, so integral 1 by t dt from 1 to x is nothing but the natural log of x. So now, so not only that, see now what I have got a series representation for e power y. So let us just quickly look at, so you would have used exponential functions a lot of times. But now basically we just give a look at it. Till now we were just talking of e. Now we have come to e power y all of a sudden with y a real number. What is that? So we'll just look at a more general scene. If b is a positive number and x we consider as a natural number, what will be b power n? It will be product of b multiplied n times. B power minus n will be product of 1 by b multiplied n times. And b power m by n would be nth root of b power m. That we all understand very well. And if x is a real number, so I write the decimal representation. So, irrational number. So what is the difference between rational number and irrational number when we have the decimal representation? So it will be either, yes. So here, now what I do is, I take xn to be w and I just truncate at the nth decimal place. So w dot d1, d2, dn. That's a rational number, good enough? So I can consider b power xn and I take this b power x as limit as n goes to infinity b power xn. That we can have intuitively, that is the best thing that we can have. Again, I'm not going to technical details, one can prove that this is limit exists, although, but we are not going into that. So now we have that b power x and now we change our gears and we consider the problem of differentiation. So I have the function in hand, b power x, and I want to differentiate it. That you all would be knowing how to differentiate this, yes? So this is limit b power x plus h minus b power x by h as h goes to 0. And I can take common b power x that is not dependent on h. So this is b power x times limit b power h plus, minus 1 by h. And this I take this limit I call as k. Now see, this is a constant. There was no x appearing in the picture in the limit. So this is independent of x, but obviously dependent on b. So what I have that the derivative of b power x is a constant multiple of b power x. Yes? And what will be the most beautiful thing to see? That the derivative of the function is exactly equal to it. So that means k is equal to 1. So what will happen if k is equal to 1? In that case, we'll see that again my e comes up. And that you all would be knowing that derivative of e power x is e power x. But let us just see how does e come up here. Again, we just have an idea. I'm just ignoring all the technical details. We just have that how do you intuit and how do you have just apply the idea. Then it's a different thing to apply epsilon delta and all those things. So you have limit. So if you want k is equal to 1, so that means limit b power h minus 1 by h is 1. And therefore for small enough h, you have b power h minus 1 by h is very close enough to 1. So that means b power h minus 1 by h is approximately equal to 1 for small enough h. So now this is b power h. So if I solve for b, I get that b is approximately equal to h plus 1 by 1 plus h whole power 1 by h. And so basically, so this is for small enough h and b is, so then b is close enough to this, so this quantity is close enough to b for small enough h. So that means that my limit 1 plus h whole power 1 by h is equal to b as h goes to 0. Now instead of taking h, I can just plug in 1 by n, because as h goes to 0, as n goes to infinity, 1 by n goes to 0. Yes? So I see that this is limit 1 by 1 plus n power n as n goes to infinity is b. And what is that limit? Is e. So I have got that that again, when my derivative of an exponential, the derivative of the exponential function is exactly equal to it, the function, then this b is nothing but e. So therefore, this is called a natural exponent. Something that, so what we have seen that the derivative of e power x, it is equal to e power x. But in fact, you will see in differential equations that the converse is also true. In fact, e power x is the only function up to constant multiple that is equal to its derivative. That means if fx is equal, if f prime x is equal to fx, if and only if my fx is some c times e power x. So you will see that, see, the function that I am showing in the figure of that graph is e power x. The slope at x is equal to 1 is e. The area that I am, the colored portion, that area is also equal to e, in fact. So we have now, so there the e comes. Now let us see, we have been talking of e. Who gave us this number, the symbol for e? So, okay. So here Euler gave the symbol for e, and so see, e, the notion came up in 17th century. Now almost after 1 century, the next century, Euler actually used the symbol e for this constant. Otherwise, people were using different constants, and Euler was a great mathematician, very respectable. So he immediately this basically became the standard notation for e. So in 1731, Euler gave this notation, and sometimes it's also called, because of this, Euler's number. So now, as that this was the first thing, in fact, you all pointed out that e is an irrational number. So how do you see that e is not an integer? So that's an easy thing to see. Again, we rely upon the series expansion for e. So we can see that e is strictly greater than 2. And because my 1 by 2 factorial plus 1 by 3 factorial plus so on, I can just take 1 by 2 common, and I have this 1 by 1 plus 1 by 3 plus 1 plus 1 by 3.4 plus so on is less than equal to the series 1 by 3 power k. So again, the similar idea that I've used in the beginning of this talk, this gives me that e is less than 2.75. So obviously, if e is greater than 2, less than 2.75, it cannot be an integer. So I have that e is not an integer. How do you show that e is a irrational number? So let us just assume that e is a rational number. It's a very simple proof. That's I think the rigorous proof that we are doing in a way. But it's very simple. So what? Now see, let us take e to be p by q, where q is greater than 0, and consider the series expansion for e. And what you have, q factorial p by q. So what do you get? The left hand side is an integer, q factorial times p by q. That is q minus 1 factorial times p. That will be an integer. The right hand side, let us look at. So you are multiplying q factorial with each of the term. Till you get 1 by q factorial, that will be all integers. I have written those. Then come this 1 by q plus 1 factorial, 1 by q plus 2 factorial, and we end up at the integer, fractions. But now one can say that, okay, the sum of fractions can be an integer. But now here again we apply that, again we apply that the comparison between the geometric series. Q cannot be 1 because p by q cannot be an integer. So q cannot be 1. Q has to be greater than or equal to 2. So q plus 1 has to be greater than or equal to 3. Again, I compare it with the series 1 by 3 power k, and I get that that portion, that is really something less than 1 and it is positive, so it has to be a rational number, so a non-integer. So what do you get? In the previous slide, if you look at, that is an integer, the left hand side is an integer but not the right hand side. Therefore, E cannot be a rational number. Now, Euler did it with a different way. So he gave the continued fraction for E. Also, so he just gave this, and if the continued fractions are indefinite, that signifies that the number is irrational, and he gave an indefinite continued fraction, so that he has an indefinite continued fraction. Also, his gate, so it's not only that E is a irrational number, but now see, root 2 is an irrational number, x square, but it is a root of polynomial x square minus 2. But E is also cannot be seen as a root of a polynomial with integer coefficients. So it's a transcendental number. One more thing that Euler did was he extended the thing to the complex numbers, and we have the beautiful identity that is called Euler's identity, e power I pi plus 1 is equal to 0. Now so here these are more or less as exercises. Here we'll see how my E occurs in various contexts that look very unrelated to E. So let us then let me just, so maybe we can skip those, and I'll just have so these are the 4 small calculus problems and probability problems that you would have seen that come up, that E comes up somewhere or the other, in some form or the other in those problems that look very unrelated to them. But now I just give you a paradox. So you can see now we have e power I pi plus 1 is 0. That was the Euler's identity. So if you have this square it, this e power I pi is equal to minus 1, you will get e power 2 I pi, and that you know also. E power 2 I pi is equal to 1. Now you just multiply E on both sides. E power 2 I pi plus 1 is E. And then you have so E is also e power 2 I pi plus 1. So what the left hand side E we write as, so e to the power 2 I pi plus 1 and to the power 2 I pi plus 1. That will be E. And now you have that e to the power a whole power b is e power ab, and by that thing you just have e power this. So you get e power minus 4 pi square is equal to 1 finally. And you know E is a 1, 1 function. So that will give me that minus 4 pi square is 0. So we all know about E is irrational. Is pi is 0, pi is 0. So I end with the note that just think of it. Obviously, there is a flaw in the whole argument, somewhere or the other. Try to find it. Obviously, we know that pi is not 0. We know the value 3.14. So if pi would have been 0, there would have been nothing. Almost all the mathematics would have collapsed. So think of it. So we end with this. Thank you.